This
Perfect.
meeting is being recorded.
This meeting is being recorded. All right, let's get on to hacking satellites. So, as I said, when you start hacking satellites, I always recommend starting with NOAA 15, 18, and 19. Because basically what you're going to do is you're going to tune an FM radio to record the passing satellites going overhead, grab the audio, and then you're going to decode the audio. So let's see how this works. Let me share my screen. See, share screen. Here we go. I'll zoom into each window individually, but I just want to, I don't know if this is going to work, and I don't want to go through the process of doing this the right way, but let me see if I can't let you hear what it sounds like when you record audio from one of those NOAA, the National Oceanographic and Atmospheric Administration satellites, weather satellite audio sounds like. So hold on. So I'm going to put my headphones up to the microphone. Maybe you'll hear it, maybe not. I don't know if you heard that, but it does sound a little bit like beep, 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 and a metronome, tick, tick, tick. And all those beeps and that metronome are just scan lines of an image. So we can decode that image and get images from the weather satellite. And by the way, I did this using a $20 SDR and a trip to Home Depot, and that was it. So to get started, decoding images and decoding data from satellites is not as daunting of a process as it might sound. So let me zoom into this window here, which is NOAA-APT. It's a piece of software for decoding that audio. Let me share, let's see. Here we go. So when you open up NOAA-APT, you're gonna select an input file. And we're just gonna select the input of the WAV file that you just heard. So just the audio file, okay? So we just recorded some audio using a radio. And we're gonna just click decode. Okay, it's already done. We'll go to processing. And we're not gonna work with any of the options here. You can play with it if you want, but we'll just say process. And over to the right is the image that we decoded from the passing satellite overhead. So this is the coast of California. Oops, let me see what someone says something. I see this audio is in the future. Oh, no, the audio is actually from the past, Sam. It's from a long time ago. So this was from a very early setup that I just happened to have. And so you get the image to the right here, and you can save the image, colorize it, and it's just black and white because this is a very basic, old standard for sending images. But you get these low resolution black and white images out, and it's actually two cameras. So when you're working with weather satellites, you'll find that they record in very specific wavelengths and then set out data in like 1 or 2 or 3 different channels. I got another image. I can't believe I didn't even see the flag. Yeah. All right. I don't know what file you're talking about, but yeah, no, that's how you decode weather satellites, just using a standard radio, FM, receive the audio, and then you can get an image out. So let's go back to the presentation. Stop sharing. Let's pull up that again. All right. So that's all we did. We just listened to the radio. We got an audio signal. Audio signals happen to be an image, actually. And so it took seconds to decode the image once we recorded it. Yep, and here's the image we recorded again. And this is, you can actually see the coast of California. So I was in San Francisco at the time. And so this is, you can see the San Francisco Bay Area sort of in the center there. And since then, I've gotten a lot better at decoding these satellites, but this was an early attempt. And so if you're just beginning, to work with this stuff, this is sort of what to expect. Sort of a lot of fuzz, a lot of graininess, but definitely it can be done with some very cheap materials. You can do it with your students, and yeah. So let's talk a little bit more about digital radios. I've mentioned software-defined radios a lot, and that's because they are so key at any satellite hacking. So The problem with radios to the computers is that we're dealing with USB ports. Now, USB ports operate, I forget how fast, like 200 megahertz, 400 meg. It's 100 meg. I forget the exact specs, but it's not that high of a frequency compared to the radio waves that we're receiving, which might be 1 gigahertz or 2 gigahertz. You got to pass that data through the USB port. And so the way that software-defined radios work is that they essentially convert the radio waves, the raw radio waves, into like a stereo audio signal. And this is done through some. So essentially, what you can do is if you, for example, take a sine wave or a cosine wave and mix it with any incoming signal, what you get are two waves out. You get the difference and the sum of both of the waves and frequencies. So, but let's say we just want, but we want to lower the frequency so we can send it through the USB ports. We can then send the output through what's called a low pass filter to get rid of the sum and just get the difference. And that way we can convert something like a 10 gigahertz signal into something like, 20 kilohertz, which is within the it's the upper range of human hearing, or even like 10 kilohertz. So yeah, you can downgrade this high frequency signal into essentially audio territory. But there's a trade-off. There is some loss of information when you do this. However, smarter people than me have figured out that over here, this triangle thing is an antenna. The antenna thing goes to an amplifier. The amplifier sends the incoming signal to two mixers. One mixes it with a cosine wave, and the other one mixes it with a sine wave. And so, of course, cosine and sine are 90 degrees apart. And so we call this in phase and quadrature. And when you have both of those signals coming in, you can completely reconstruct the original signals. That's why you get a stereo audio output essentially from these SDRs. So you have an in phase signal and a quadrature, two audio signals coming in, and you're able to transmit, like I said, 10 gigahertz, 20 gigahertz frequencies straight through your USB port, no problem. And that's how all SDRs work. So you have your Wi-Fi router that has an SDR that's throwing things into in phase and quadrature. You have, your cell phone, LTE, 5G, 4G, doing the same thing. Any digital electronics is doing this. They're taking an incoming signal, mixing it with a cosine and a sine wave that's slightly below or slightly at the frequency they're trying to receive to get this lower frequency signal that can be essentially processed by, your software. And like I said, in phase and quadrature. So cosine is in phase and sine wave is a quadrature, 90 degrees out of phase. And you can then, now you have two signals coming in, and now you can plot the signals coming in into essentially a quadrature plane. So you have I on the horizontal plane and Q vertical. And so depending on what you're getting in, you can plot it on this plane. And that's really useful because we can encode data that way. So let's say you have your quadrature and your in phase signals coming in through your SDR, and you see at any given point, you might have a wave coming in where both I and Q are 1, and that way you have 1 and 1. That encodes 1, 1. Then maybe you have I being 0 and Q being 1 or being high. That's 0, 1. And let's say you have, both I and Q being low, below the 0 point in the wave. That's 0. And by the way, the way you figure out where I and Q goes is purely in their phase. And this is why so many digital electronics use phase modulation, is because of this thing right here. Because the SDRs, they down mix the signal, and then you can get this nice graph here to encode data. And if you use phase modulation, you can get this nice graph. And like I said, every digital transmission uses this. Your Wi-Fi, your cell phone, all of them. This is how data is transmitted over the wireless signals. In fact, you can see it here in a program called SDR Sharp, which if you get an SDR, you're probably going to use this program. This was an example of me decoding a digital signal from a passing Russian satellite overhead called Meteor-M2. So at the bottom left, you see that same graph where you see that the signals sort of line up in the 4 quadrants, and you can use those 4 quadrants to figure out, what data is being sent out. And of course, I had a little bit of trouble overhead, but I was able to get parts of California in this digital signal. And that's where most satellites are today for sending out data, is they use this quadrature type, or sometimes they're not even that complicated. Sometimes I'll just use 2 points called, bi instead of quadrature, instead of quad. But that's how digital data is transmitted. And this is something called, like I said, low resolution picture transmission, but it's still better than the automatic picture transmission that we saw earlier. And like I said, if you get a good signal, you can code way more data. And this is how we're getting really, really fast Wi-Fi. So like I said, where the quadrant that the in-phase and quadrature sort of signals go into is based on phase, but I guess where it lands in the quadrature, I used to say, like, if it's close to the center point or far away, has to do with the amplitude. So we can encode amplitude and phase into something called the quadrature amplitude modulation. And we can start encoding 4 bits per module, or per quadrant, depending on the amplitude. And we don't have to stop there. If you get a good signal, you could go Q64, Q128, Q256. And in fact, what your Wi-Fi router is doing behind the scenes is it's looking at the signal strength and then deciding, okay, well, the signal strength is really bad right now, so we'll use like 2 quadrants. Or now the signal's starting to improve, so we'll use like 4 quadrants so we can get like double the data. Or you'll get a really good signal and you'll get, oh my gosh, 64 bits of data per quadrant because we got a really good signal, no noise, perfect. And now let's talk a little bit about the deep space network. So we all know about the internet, right? So all the computers in the world are linked up via the internet. And low Earth and geostationary orbiting satellites sort of do their own thing. But anything further than that, that gets put on the deep space network, which is like the internet for deep space computers, which is awesome. And by the way, if you have a large piece of land that you can put up like a 3 or 4 or 5 meter dish, you can get on that deep space network too. So there's nothing stopping you. It is open to everyone, and there are lots of amateurs doing it. So the way it normally works is that there are 3 main sites. So you have a site in California, a site in Australia, and a site in Spain, and they're all like 120 degrees apart from each other. So at any given moment, the main 3 deep space network, like ground station, have a 360 degree view of the sky. So anything out there, they can receive at any given moment. So for example, the moon landing was part of the DSN. Anything further than geostationary orbit is part of the DSN. So this has been around forever. And so you can imagine there are some maybe security vulnerabilities in this. Think about that. So the TV signals from the moon landings would go through, depending on where it was, go through either like Australia or through California, the Goldstone tracking facility in the Mojave Desert, or so on and so forth. And then that would get transmitted back. And actually it would go from the lunar lander to one of the orbiting Intelsats to one of the ground station. And there's a lot of, and I misspelled landing. It's not Lnading, it's landing. And you'll see a lot of that in the DSN, where there's a lot of sort of proxying of data. So data will come in, it'll get held, and then sent back out. And this is the very simple example of that. And you can actually go to the DSN website, and we can do that in a little bit, and see what each site is collecting at the moment. In fact, let's do that. Let me switch back here. Let's go to eyes. Let's go. DSN. HTML. Okay, here we go. All right, I'm going to share my screen. All right, so we can see what everything is looking at right now. So in Madrid right now, it looks like it is looking at a spacecraft called Akatsuki, which is 221 million kilometers away. It must be a Japanese satellite. This one is sending and receiving data from the Advanced Composition Explorer. And this one is getting spacecraft from SOHO, which is a solar probe, which is the one, I think it's getting close to the sun and, getting readings. Oh, here we go. Goldstone is currently getting data from Mars Odyssey. So it's getting data from Mars at the moment. Oh, here we go. So the Australian site is currently locked into Voyager 2. That's awesome. Oh, here we go. So James Webb, the Australian site right now is currently grabbing the, so if you're wondering where the data path for the James Webb telescope is right now, currently the James Webb Space Telescope is being directly connected to the Australian website, the Australian dish 34 of the Deep Space Network. And it's just currently downloading data, probably images that we're going to get in a few days. And we'll look at that in a bit. And in the Australian site, the Australian receiver is also looking at something called the Double Asteroid Redirection Test, which I believe is part of preventing our at the end of the world, which is always good. So yeah, so now we know the path of the data coming in from the James Webb Telescope, which if you were hacking the James Webb Telescope, that would actually be useful information because those lines would probably be coming out of that facility right here. Let me stop sharing. And let me go back here. All right. So now we saw how the DSN roughly works. And so the Deep Space Network works on delay-tolerant networking. So the problem, of course, with these long-range networks is that sometimes you'll be able to get a signal through, sometimes there'll be an intermission, sometimes you can get part of the data through. And so you have to be really tolerant to these types of interruptions. And so our normal internet, our normal networking uses TCP/IP. The Deep Space Network uses DTN. And you can actually set up your own DTN network at home using Ethernet cables. I mean, it's just a similar protocol, like AppleTalk or one of those other types of protocols, but it is specifically designed for very poor network quality, essentially. And as you can see in this diagram, I didn't make this diagram. This is by NASA. The data sort of goes through a bunch of different points, and then eventually sort of makes its way back. So you might have, for example, the Mars lander send data up to the Mars Odyssey. And we saw that just a second ago at the DSN website. One of them was looking at the Mars Odyssey, which is an orbiting satellite around Mars. And that will then send data, maybe to the moon or maybe to an orbiting satellite around Earth, which will eventually, when it gets a good contact with the ground station, relay that message to the ground. And like I said, you can get on yourself with some moderately sized dish. Ideally, you'd want a big dish, but you can take a 2 or 3 meter dish and get on yourself. There's uhfsatcom.com, which is a great resource, by the way, has a bunch of info on this if you want to do this yourself. So you can get on that quote unquote internet, the internet of outer space yourself, if you have room. and see what's being sent and received. And we saw earlier that all the data being sent and received, and to demodulate it is just using the quad Amplitude modulation type decoding. Okay, so let's actually take a look right now before we move on to FPGAs, because we did just talk about the Deep Space Network, and James Webb is in the news. I just want to take a look at some of these images and take a look at the James Webb Space Telescope for a second. So let me share. So the James Webb Space Telescope has its own homepage, of course, and we can actually view some of the first images that are coming in. And so, of course, one of the famous ones right now is the Southern Ring Nebula, which, as you can see here, is, oh, you can't see that very well. And I don't know if am I sharing correctly? Hold on, let me try this again. There we go. I don't know. Let's see, view, copy image link. Okay, so now so this is a left and right image of James Webb and an older telescope. I think it was the Hubble. And at the left here, you can see a nice little galaxy. And you can see in stunning detail this nebula. Now, I should point out that most space vehicles, especially the James Webb Telescope, are not shooting in, visible length wavelengths. So these are false color images, but even still, you get some very stunning details compared to what we were able to get before. Let's go back. No. Okay, there we go. Let's see, what else do we have here? We have, the first deep field, which is always a good thing to look at. So, of course, when Hubble went into space, its most famous image was a deep field. And this deep field image is very spectacular because it's looking back even further than, oh, I messed up, hold on, copy image. No, copy image location, copy image link, yeah, paste, there we go, okay. So besides the gravitational lensing and all that fun stuff, the James Webb Space Telescope is actually capable of seeing much further into space than Hubble. So what you're actually seeing is also much further back in time. In fact, one of the things that the James Webb Space Telescope is going to be able to do is look at the very first stars that were formed. And of course, to commensurate the launch of the working of this James Webb Space Telescope, we have here one of the first deep fields, which is very nice to see. And of course, we see some redshifting as well, because these objects are very distant. And these are not stars, these are galaxies. So let's go back to some more James Webb Space Telescope. Cosmic cliffs. Always a good thing to capture in stunning detail. Now, one of the interesting things here I want to point out about this image is actually we can tell a little bit about the spacecraft itself from the images that it takes. So we already know that, or you should already know, that the James Webb Space Telescope is an infrared, and you can do all that kind of stuff. But notice a lot of these bright stars have these points. Like there's it goes up and down and side like this and that, and you see this a lot in Cassegrain type telescopes or reflector type telescopes. What's going on? Well, let's take a look at the James Webb Space Telescope really quickly. James Webb Space Telescope, and we'll go to Google Images. Okay, here we go. No, open. There we go. Okay, so this is a good image of the James Webb Space Telescope. So notice there's this arm here, this arm protruding to the reflector. That's where those lines are coming from. So go away. If we go back to the image, this image, where you see the lines darting out from the stars, that's actually caused by by these arms. And you'll find that they're also in the same angles. These arms are in the same angles as you'll see from the artifacts here in this image. And the reason why it's sort of doubled on both sides is because there's a reflector in the back that, reflects the image up and down depending on, the angle it's coming in. What's really kind of interesting about the James Webb Space Telescope in particular is that the mirrors themselves can actually be adjusted, which is absolutely phenomenal. One of the issues, of course, with Hubble was that the mirror was not perfect at launch and they had to replace the mirror. Now, James Webb, of course, is in the L2 Lagrange point, which is how do I explain Lagrange point? It is a place where sort of gravitational forces balance out. So basically, it's sort of hovering in the same spot in relation to Earth's orbit all year round, sort of on the far side of the Earth and Moon. And it's, replacing the mirror would be impossible. So the mirrors can actually fix themselves, which is awesome. And you'll find that a lot when you do space hacking is you'll look at images of spacecraft or images from spacecraft, and you'll be able to infer a lot from it. So once again, let's look at one of my favorite spacecraft, or I should say Marscraft, which is the Ingenuity Mars Ingenuity helicopter. So this is the helicopter that flew on Mars a few times, and is still flying as far as I know. Images. Here we go. Here's a nice image. Open up. Okay, so this is an image of the helicopter. We can tell a lot about it based on this image alone. There is, of course, solar panels on the top. These are carbon fiber blades. Now, this image actually isn't too good because it doesn't show the antenna, but here we go. We can see the antenna on top, and we can actually use the size of that antenna to deduce what frequency it's broadcasting at. And it's probably broadcasting at, I think I calculated around 900 megahertz, meaning that what it's doing is it's actually not broadcasting directly to the satellites. And we can also tell it's not broadcasting directly to the satellites because it's vertically polarized. What's happening is that it's sending data to the rovers, and then the rovers are then bouncing that data to the satellites overhead. And now what's really interesting is, can we get an underside view of Ingenuity helicopter? I wish I had this ahead of time. Because I saw an underside view of the helicopter, and I was able to source some of the components. Shoot. Is this it? Nope. But anyway, I was able to figure out some of the components that the helicopter is using. And it was this thing right here. Oops. Yeah, it's this device right here, $129. So the way that the Mars Ingenuity copter works is that it has a LiDAR below the spacecraft, and that's how it detects how far it is, above the ground, and can land safely. And I found the component they were using for the LiDAR, and it turns out it was a $130 SparkFun LiDAR, which apparently works just fine. And there's the website, and you can get the schematics of how it interfaces with the spacecraft. But they literally just put like SparkFun components in this multi-million-dollar drone, because why not? There was also some other fun things in that spacecraft as well, like they were using a smartphone processor, like an ARM processor and stuff. I mean, it was absolutely ridiculous that they got that flying on Mars. But yeah, so there's a lot you can do just by looking at the images of spacecraft and just sort of deducing little things and then working out stuff. And of course, for a spy, this is really important for a spy craft, because if you have I'm going to stop sharing. If you have a satellite in orbit that is going to be spying on different countries, you can actually figure out what the resolution is based on the what you can see from the camera itself. So if any images of the spacecraft gets out, you can use that to deduce what the aperture is and what resolution you can get on the ground and what the spy satellite can resolve essentially. And there are actually techniques to get even more resolution using things like, once again, radar and LiDAR and stuff in space. But still, if you just get a look at the spacecraft, you can tell a lot about the internal technologies and what's going on, as well as the data you get back from the spacecraft, as we saw with the James Webb Space Telescope. So let's continue with the presentation and talk a little bit about FPGAs. I'm not going to go into too much detail, but it is important if you do go into space hacking that you know a little bit about what these are and their role in spacecraft. So like I said, if you have something in space, you're just going to make it once. You don't want to go to a circuit factory, get a special circuit made just for your spacecraft, because it costs about $500,000 to make one silicon chip, and then it costs about $500,001 to make two, and $500,003 to make three. I mean, it's an economy of scale. But you can get these chips called field programmable gate arrays, which essentially allow you to make your own digital electronics on the fly and reprogram them. And these are used a lot in spacecrafts because, like I said, these are one-off things. And if you can get access to the spacecraft, it is technically possible that you could rewrite the FPGAs to sort of rewire the spacecraft itself. And so that is something I'm really looking forward to trying out in the future, is looking at the ways that you can actually hack the hardware itself, like rewrite the hardware of spacecrafts, not just upload software, but hack the hardware itself to like do something completely new. And so the way FPGAs work is that you have these configurable logic blocks, which are essentially these blocks that you can say, oh, you're going to be a AND gate, or you're going to be a latch, and you can connect it together through all these switch matrices, and you can get any digital circuit you want out. And in fact, here's an early FPGA, and it only had a few logic elements, but you can actually almost kind of sort of see it with a microscope. So sort of, there's like 4 quadrants of 4 here, and nowadays most FPGAs contain thousands and thousands and thousands of logic elements, but early ones contain just a few. I'm not going to do a demo. And yeah, so operating systems in space. So one thing that you might be wondering, and a lot of people wonder, is what operating system do spacecraft use? Do they use Linux? Do they use Windows? I hope they don't use Windows. The Mars helicopter we saw did run Linux, and that is actually very rare. Most spacecrafts do not run Linux, and they do not run Windows. They run real-time operating systems. And so the idea behind a real-time operating system is that you have complete control over the timing of your processes that run on the system. So you say, run task 1, and then I want you to not, interrupt task 2, wait until task 2 is done, then run task 3, etc. And that's really important for spacecraft because, because if you're running like a thruster, and you have to be very precise about the timings. Like you want it to run specifically for 3.146, why am I doing pi? 2.67972 seconds or something. I don't know. But you just need it to have a very specific amount of time that your thrusters are going for. You don't want any process coming along saying, oh, I need the processor for a little bit to look at TCP traffic or something. No, you need to be able to control that timing exactly. And that's where real-time operating systems come in. And so the most popular one we see on spacecraft is something called VxWorks, which is kind of like a Unixy interface. It has a lot of features I don't see in a lot of other real-time operating systems. It's very full-featured, actually, but it is straight out of the 1990s. This has been around forever, and it's not very it's not used a whole lot outside of space and a few niche applications. So there's a lot sort of going on under the hood that I imagine there's just, it's a mess. But of course, if you, and VxWorks is a paid product. FreeRTOS is the new hotness for real-time operating systems. It's actually made by Amazon. And so actually, when I was interviewing for the Kuiper project, and I knew that this was a satellite made by Amazon, I told them, yeah, you're running FreeRTOS on there, aren't you? as the underlying operating system. And they're like, yes, we are. And that and that is just, like I said, free real-time operating system that you can run actually on anything. And if you want to try it yourself, you don't have to get a specialized platform. You can actually run FreeRTOS on top of like Windows or Mac OS and just try it out and see how it works. I got to warn you, though, it is a pain to use because you are managing every little thing in the system. Like, one of the nice things about modern operating systems is that everything is sort of hidden, and Windows does its own thing, and Linux just makes sure everything runs fine under the hood. When you're running a real-time operating system, you're saying, very specifically, load this process, or you might compile the process with the operating system, for example, like run them together. I mean, it's a mess. And then you have to be very precise about how you want it running and how you want the timings while it's running. It's important for spacecraft, but there's a reason why you would never find something like FreeRTOS on a user's desktop. And Sam, how are we on time? Do we need a break? It's been about an hour.
I don't think so. I think you can just keep going.
Okay, perfect. All right, so there's also a lot of open source software used in spacecraft and on the ground that you should know about, and you can play around with. You can download, use, have fun with, have a good time. So mission control software. So if you ever seen those mission control systems at NASA or at even SpaceX, they're probably using something like YAMCS, which is how they sort of display the information coming in from all the different satellites and rovers and space missions. OpenMCT is another version, and is very similar to YAMCS. I think it has a slightly nicer interface. But once again, this is just for mission control. You can download this, make your own mission control setup. There's a few other mission control things you can download as well. But they all do the same thing. They all just display information about what's going on, and you get a sort of at-a-glance display of your mission. And now we're getting to the big one, the Core Flight System, CFS. This basically runs all of the spacecraft. Okay, there's very few spacecraft that are not running Core Flight System. I don't know if anyone's ever worked with drones and ArduPilot, and how every drone somehow has ArduPilot on it. If you do any real stuff with drones, you're running with ArduPilot. With spacecraft, it's the Core Flight System. It is this piece of software that was developed decades ago, that was designed specifically for spacecraft. It's on all the spacecraft. And basically what it is it's a way to tie different payloads together. It's hard to explain. But let's say you want to write software for a system like a camera that you put on a spacecraft. You can then interface it on the bus using the Core Flight System. And then let's say another spacecraft uses that same camera. You can then, even if it uses a different processor, you can port that software over so you're not rewriting stuff. And Core Flight System is sort of the glue that sort of makes, space programming of space satellites, space equipment possible. There's also Core Flight Executive, which is the library that's underneath it. And actually, let's check out the GitHub pages right now for that. Let's see, let's share my screen again. Okay, so let's close this out. And let's go to the Core Flight System GitHub page. Yeah, NASA CFS. So it is. You can download it yourself. And there is a CFS user's guide, app developer's guide, training documentation, and an overview. And some of these overviews are really good. You can actually get started right away. In fact, they have like CFS VMs you can download. Core, I can't find it, for flight system VM download. Yeah, it's OpenSatKit is, you can use OpenSatKit with NASA core flight system to create sort of a fake satellite that you can play around with and play around with core flight system. I forget the name of the VM that they offer, but there is like a training VM that you can get with core flight system. Let's see. So yeah, so you have this is what a spacecraft would look like, a typical block diagram. There's a lot of things going on inside. And so you want a way to interface it. And that's where core flight system comes in. And so you have like the core flight system applications, and then some libraries, and then the core flight system executable, which is the library itself that sort of binds everything together. It's like a framework. It sort of binds everything together. So you write an app and you compile it against the core flight system, core flight executive, upload that to a spacecraft running something like FreeRTOS and CFS, and now you have software running on your spacecraft. Let's see if we can't find a good example of the bus. The message bus, here we go. So the most important thing is the message bus. Here we go. This is the logogram bubble diagram of the message bus. So the way it works is that you have a whole bunch of software running on top of CFS. So you have a lot of standard stuff too, like the file manager, the CFDP file transfer module, which is very important, by the way. And all these modules sort of communicate with each other on this software bus within core flight system. And now what's really interesting is that a lot of like I said, there's the CFDP file transfer system on all core flight system. And that basically allows anyone to upload files to the spacecraft, assuming you can, you know, the encryption keys. And what's interesting about that is that you can then run what you upload. So you can compile a CFS application, upload it using the file transfer application, and then execute it using either like the scheduler or there's another CFS app that you can use to essentially run CFS applications, and you just upload them as SO files, essentially as shared object files, and then they can get on the software bus. And there's no differentiation, right? So every application on CFS, this is old software, every application can see what every other application is sending over the message bus. So, and everything's running as root on the system. So this is what is running on everything in space, is this core flight system developed in the 90s, single message bus. It essentially runs a TFTP server that you can just upload an SO file to. And then you can run that SO file, and that SO file is running as root then and has access to the entire message bus, can send messages and read messages from any other component on the system, including the memory manager. So you can dump memory of any process on a spacecraft, just like that. You don't need any special permissions, nothing. It's fantastic. I love CFS for hacking. And the reason why this is, of course, is not because the engineers are lazy. It's because a lot of the times when you're sending up spacecraft, you have to radiation harden the components. And that means you're not using the latest and greatest Intel or Apple Silicon or whatever's coming up the stream, RISC-V. They're using PowerPCs at most, like old PowerPCs running at like 100 megahertz, 75 megahertz, 25 megahertz, like really old hardware. They might have 256 kilobytes of RAM or 2 megabytes of RAM. I mean, these systems just don't have much to work with. And so throwing, user levels and everything on top of everything was just too much. So it's all very simple. And once you get a foothold on CFS on some satellite, that's it. I mean, you've taken over that satellite. And yeah, you can, like I said, there are VMs you can download with Core Flight System and some, simulated satellites that you can play around with. And yeah, and like I said, CFS runs on top of RTOS, which they talk about here. Actually, let's take a moment. Are there any questions? I know I've gone over a whole lot. It's just so interesting. Doesn't look like there's a whole lot of questions. All right, then let's continue then to look at the next part of these slides. So spacecraft can generate power through two ways, either solar panels or through nuclear batteries. And now the nuclear batteries, are there any ways, are there any plans for Core Flight 2.0 or anything new? As far as I know, no. No, absolutely not. So let's go back to the GitHub page. In fact, one of the big things about Core Flight System is that it's meant to be as backwards compatible as possible. So let me share my screen here. So this is the Core Flight System homepage. And as you can see, it's been around forever. So the FM is the file manager, et cetera, et cetera. But it's been around forever. And their main big selling point is that it hasn't changed much over decades. So what you write a decade or 2 decades ago still runs perfectly fine today. And so they have, in fact, not only do they have no plans for a Core Flight System 2.0, they actively do not want to, update Core Flight System much at all or change it, because the entire point of Core Flight System is creating the stable, plane of that people can write software for different satellites and then have it be interchangeable. And if they write Core Flight System 2.0, it breaks, it breaks the paradigm. And so as you can see, this GitHub was last updated yesterday. Core Flight System is still in active development, but they're not going to change the APIs or anything at all, because that would, like I said, break the core tenet of Core Flight System. Let's see, when was the last build? Releases. 10 days ago was the last release of Core Flight System. So yeah, Core Flight System 2.0 is not in the works. This is actually for Core Flight Executive, but yeah, this is all still being actively developed. And yeah. Any other questions? And yeah, there's nothing new that I know of. There might be something new with private aerospace that they're working on separate, but the standard Core Flight System is not being updated anytime soon. All right. All right, so let's look back again at power on spacecraft. There are 2 ways that spacecraft can get power, which is either through nuclear batteries or through solar panels. Now, solar panels are, of course, the most common ways to generate power on your spacecraft. But if you have some spare plutonium, you can essentially create a crude thermal battery by sort of heating up thermoelectric devices that will generate a current when exposed to heat. So when you have a big clump of plutonium, it's just so radioactive, it just glows red hot all the time. So you can just sort of extract a little bit of energy from that. And that's how Voyager, anything that's deep space, far away from the sun, works. And it's Voyager 1 and 2, New Horizons, they all have plutonium batteries. And One of the big problems, of course, is that on the ground here, we are moving away from nuclear fission as an energy source. So we have less and less plutonium to put on spacecraft. So that really limits our ability to do deep space exploration. But there is a fun way to make nuclear power at home that you can do with your students that might be fun. And so I did want to share this. So this is the Radioisotope Thermoelectric Generator, the RTG, that you find on things like the Voyager spacecraft. There was also one on a Mars lander, but they're very rare. You take plutonium, and then you sort of extract excess heat from and turn it into electrical current. Of course, we can't really get plutonium at home. This is what plutonium-238 looks like. It literally just glows red hot all the time. Has a half-life of 87 years. So that is a big problem when you're dealing with spacecraft where you have it going out into deep space for decades. So there is a continual power loss because of the half-life of 87 years. So you get, less and less energy. But for most space missions, it's fine. And by the way, this amount of plutonium that they put in spacecraft are like years and years worth of plutonium waste from nuclear reactors. It's a lot. A lot of the plutonium generated just goes straight up into space, which is a good place to put it. I mean, it doesn't do a whole lot of good here on the ground. And this is what a real RTG looks like. It's very large, and it just contains plutonium and generates power. So let me introduce you to an electronic component called the Peltier Cooler. So this is a thermoelectric device. You often see it on heat sinks for CPUs. So overclockers that like to overclock their PCs sometimes use these. And basically they're weird hot/cold place. So you have a hot side and a cold side. And the hot side gets really hot and the cold side gets really cold. And you get this to happen through passing a large amount of electric current through it. And you can use that. So if you cool off the hot side, you can get the cool side to be really, really cold. And sometimes you see these also in the little fountains where you get drinking water and you get cool drinking water. Sometimes they'll use these Peltier coolers. They're not very efficient, but they're small and compact, and they work on thermoelectric principles. Now, one of the things that's interesting about electronics that it always boggles my mind is that anytime something works one way, it almost always works the opposite way. And this is absolutely true with Peltier devices. So not only can you use it to use current to cool a device, you can also use heat to create current through the Peltier device. And that's the same principle of how the RTGs work. And so you can do this at home with some candles, like this setup here, where you can generate power using a Peltier device, cooling the top and heating the bottom. And another way to make nuclear batteries at home is to use tritium. So tritium is an isotope of hydrogen that is often found in things like fishing lures because they give off their own lights. And there are components you can buy for computers that will use this tritium batteries. They don't put out much power, but they last about forever. And they're very expensive. They're often used in medical devices where you just can't have a power failure. But we can make this at home. So tritium, like I said, is an isotope of hydrogen. It will release beta particles, perfectly harmless, and then decays into helium. So where do we buy this tritium, this magical tritium that's radioactive and will has all these magical properties? Well, of course, you just buy them off Amazon. You can go off to Amazon, buy some tritium lures. Actually, let's do that right now. Let's go over to. Let me share my screen. Here we go. Let's go to Amazon. My new favorite website. Tritium. Let's look for. Oh, here we go. Here's a chain key fob with radioactive tritium. But we really want fishing lures. Yeah. I don't see them. But yeah, you can get some tritium off Amazon. And so, like I said, they're constantly giving off light. So basically, they decay to the beta particles. There's basically a phosphor coating, and then they give off constant light. So you can go on to Amazon, buy some tritium. They're not that expensive. What we just saw was $31 for 3. And then what you can do is wrap them in small solar panels. So you get like 1 or 2 solar panels. And you get a few vials of tritium lures, for example. You can get them off eBay. You can get them on Amazon. And you essentially made yourself your own very small, very impractical, but very real nuclear battery. But like I said, you can do this with your students because it is completely safe. You can power devices for like 20 years as long as they don't take much power. But you can chain these together, light up an LED, and it'll light up for, like I said, 20 years. Easy peasy. Right. Sam, do you think it would be a good time for a break?
Oh, it could be. I think, yeah, sure. I'll stop recording here.
Okay.